Alright, so in this series of videos, what we're going to do is take a look at power electronics. Now, this is not going to be very comprehensive, it'll be more of an introductory level type of thing. And what we'll do is we'll start with the very basic concepts of power electronics. So in this video, we'll look at what power electronics is, some of the main concepts, I guess you can say, or the key points, or aspects of power electronics. We'll introduce a couple of concepts that are useful when we analyze power electronic circuits. And in future videos, what we'll do is we'll look at different converter topologies, we'll look at different, let's say, inverters, rectifiers, buck converters, boost converters, buck boost converters, pulse width modulation, and all that kind of stuff. So, power electronics, if you were to give it a formal definition, is often called, or often considered to be, I believe the best definition that I've heard is the art of processing electrical energy by means of switching devices. So if you've taken an introductory electronics course, you know that transistors can operate as switches if they're driven into saturation mode, I guess you can say, or triode, depending on which type of devices you're working with. But in this set of videos, what we'll do is we'll draw these transistors or switches as transistors, but we'll analyze them really as ideal switches. So let's start with the ideal switch. So what is the ideal switch? So the ideal switch, an ideal switch, we say, has the following characteristics. We say that if it's a switch, let's say if it's closed, we say this is an on switch. I guess we can say closed here. And what this switch does is it has a voltage across it, let's say V equals 0, and it has a current through it. We just call this current I. That current I is obviously governed by the rest of the circuit, but the thing to note is that there's a 0 voltage drop across the switch when it's on or it's closed. In the event that the switch is off or open, we draw it like this. So we say this is off or open. So this is an open circuit. If it's an open circuit, we see that this current I equals 0, but this voltage V is not necessarily 0. It's something. We don't know what it is. We don't care for the purpose of this analysis or this circuit here. It is governed by the rest of the circuit. But the thing to note is that it is a non-zero value, but the current here is 0, and vice versa in the other case. So in reality, we don't have ideal switches. So no ideal switches in practice. What does that mean? That means you can never have a switch that when you turn it on, its voltage drop is 0, and that when you turn it off, the current through it is 0. You will always have some voltage drop across the switch, and you'll always have some current going through the switch when it's on and off, respectively. So what that means is on, let's say V does not equal 0, off I does not equal 0. We'll say V is small, and then we say that I is small. So you might have some small voltage drop across the internal resistance of the switch, or you might have some small current going through, we call leakage currents often. So you might have those things happening in real switches. So these non-idealities, I guess you can say, we can call them non-idealities, cause losses. And those losses are basically heat, and heat basically decreases efficiency, obviously, because you're losing power. So if you lose power in your switches, or you're burning a lot of power in your switches, you're not converting a lot of power, and you're not staying true to the actual input or the output that you desire. So practical switches. What are some practical switches? Let's look at practical switches. So in the practical switches, you have 3 main, I guess you can say. You have the BJT, you have the MOSFET, You have others too, but these are the three main common ones, I guess. And then you have what we call the IGBT. So BJ2 we know is bipolar junction transistor. MOSFET is metal oxide semiconductor field effect transistor. IGBT is insulated gate bipolar transistor. So the BJT and the MOSFET are two unique devices, but the IGBT kind of combines the two. And so we can talk about, or we can really draw them. I mean, I don't see that it's very relevant to discuss their characteristics, because we're going to assume our switches to be ideal for the most part, but we can draw them just in case you see them somewhere and you're curious as to what they are or how they operate. The IGBT, like I said, is a hybrid, so it has the gate, but the other side looks like a BJT. And we can name these devices. We have here the base, we have here the collector and the emitter, we have here the gate, the source, and the drain, and these are all N-type. So I mean, you can have P-type as well, but again, just reversing polarities. And in this case, you have here the base, you have here the gate, and then here you have the emitter, but here you have the collector. So this voltage drop, these voltage drops here that I mentioned earlier, this V not equaling 0, is basically this voltage drop across DS or CE in the cases of the bipolar devices. What else is worth mentioning here? This is practically obsolete, so we hardly ever see these used in power. These are good for low to medium power, and then these ones are good for high power. And high power, I mean, like, I think they have kilovolt range IGBTs, if I'm not mistaken, but they can't switch very fast. MOSFETs can switch very fast, but they're better for low medium power. So I think that's it for practical switches as far as that's concerned. But as I mentioned, we use ideal switches in power electronics. So if we use ideal switches, then we always want, or we always assume, or let's draw one equivalent, I guess. So we say that this is our MOSFET, let's say, but our MOSFET here is actually going to be a switch that looks like this. And if we have a voltage across it, V, and a current through it, I, then this is the current here, I, and this is the voltage here, V. And the conditions for operation here are when it's on, you have V equals 0. When it's off, you have I equals 0. All right, so those are switches. Now, when analyzing these circuits, they're usually switch mode circuits. That means they have two or more operating states based on the conduction states of the switches. That doesn't mean you have to analyze every single state, because in most cases the switches operate in pairs, and if they don't, they're periodic. So you might have some behavior, but you only have to analyze it for a single period, and then after that you can just repeat the process over, or repeat the same behavior, not even the process, because the behavior is the same throughout periods, hence the nature of being periodic. But one thing we should talk about, or two things we should talk about, are fundamental electrical circuit concepts, or really physical concepts. These aren't even circuit concepts. These are related to physics. One we call the volt-second balance. And then the other one we talk about, which I will introduce after, is called the capacitor charge balance. So in the volt-second balance, suppose we have an inductor here. That's a pretty bit poorly drawn inductor. That's a bit better, but I'm still not happy with it. Let's say this is VL. Let's say this is IL. We know that the voltage across the inductor, VL, is equal to L dIL by dt. This is first year electrical engineering, circuit theory, whatever you want to call it. And that means if you were to rearrange this, you would get IL of t equal to 1 over L, 0 to t, integrating it from 0 to t, VL of t dt plus any initial current that you may have had at this time 0. But we're saying that these are usually periodic, right? So we're going to use that periodic nature. So let's assume that the thing is periodic with Ts. Okay, so if we say periodic with Ts sample period, or not even sample period, it's just a switching period, not sample period. Switching period. Then we can say that at t equals Ts, we have IL of Ts being equal to 1 over L, 0 to Ts, VL of t dt plus IL of 0. But, and here's where we take advantage of the thing being periodic and what we know about periodic signals. So if you have a periodic signal, let's say, let's imagine that every 2 of these is a single period. The fact that it's periodic means that if this is 0 and this is Ts and this is 2Ts and this is 3Ts, we know that every period, because it's periodic, it has to be at the exact same value. So let's say this is a periodic signal, it will repeat every period Ts. That means that every Ts, it has the exact same value. Okay, that means IL of 0 is equal to IL of Ts, right? Because it must be the same when it starts at the end, and then it must be the same at the end of the period. So this is 0 and this is Ts, and they're the exact same value, otherwise it wouldn't be periodic. If that's the case, then essentially what you have is ILTS here, and this thing end up canceling. So what you're left with is the integral of VL of t dt is actually equal to 0. And this is a very important concept because, and this is exactly what the volt-second balance is. This means that the average voltage across an inductor is 0 in steady state conditions, let's say. I mean, that's something we can expand upon later, but for now, that's all we need to know. Which is exactly what we expect. Average, we relate to DC, and we know that in DC, inductors don't have any voltage drops. The DC voltage drop is 0. It acts as a short circuit, which is exactly what this is telling us. Now we've kind of proven that, whereas before we kind of just knew it. Or we were told it, I guess. The second thing we have, as I mentioned before, is the capacitor charge balance. And what this is a sort of analog to that. So it's analogous to that, but it's for capacitors and it's for current through capacitors. So we can do the exact same thing that we did previously. We can, let's draw a capacitor here. That line shouldn't be connecting. So we have a capacitor here. Let's say we have some capacitor voltage, and then we have some capacitor current. And we know that the relationship between capacitor current and voltage is this derivative relationship. And that means the voltage across the capacitor, Vc of t, is equal to 1 over c, 0 to, let's say, some arbitrary time t, and you integrate this Ic dt plus any initial voltage that was on the capacitor. But then again, we can apply the same argument of it being periodic, and again, since it's periodic, we say at t equals Ts, we have that Vc Ts is equal to 1 over c, 0 to Ts, Ic of t plus Vc of 0. But we know that Vc VcTs equals Vc of 0. And so we see that, again, 0 to Ts, Ic t dt equals 0. And again, what this is again telling us is this is the average current in a cap is 0 in one period. And that should be, in the other case too, is 0 in one period. So if you have a single period, the average capacitor current should be 0 when it's in steady state. Now that doesn't always mean that it'll be necessarily in steady state, but as soon as it does reach steady state, it should be 0 again. So that's it for this video. We looked at a bunch of introductory concepts into power electronics, and really we're going to build off of these concepts in the videos to come, along with relatively fundamental electrical engineering concepts, such as the ones you've seen here. And in the next video, what we'll do is we'll take a look at an actual converter topology called the buck converter. So I hope you found this video to be helpful. If you haven't already, hit that subscribe button so that you get notifications when we upload more videos. If you have any questions, please leave them in the comments below and I'll be happy to answer them when I can. Thanks for watching, and we'll see you in the next one.